In this lecture about universal gravitation, we're going to turn our attention back into space and look at a couple of fascinating examples. The first I want to talk about is the so-called three-body problem. Now, in physics, this is actually a classic problem that's been studied for generations. And it's also the title of a science fiction novel written back just a few years ago. And it's a very well-written novel, and it's very popular. And in fact, it will be turned into a miniseries by Netflix, hopefully pretty soon. What is the three-body problem synopsis in that novel? It's a very long story, but I just want to talk about the part that has to do with this title, the so-called three-body problem. So basically, you have an alien planet. They are pretty close to us, only about 4 light years away from us. And their star system, unlike us, actually has 3 stars. Okay, we are a single star system. They have 3 stars, and that's why it's called Trisolaris. The problem with having 3 stars is that each star will attract each other by force of gravity. And then you have the so-called three-body problem. The motion of each object will influence the other 2 and vice versa. Now we know that if you have only 2 bodies like the Earth and the Sun, it's actually equivalent to a one-body problem. All you have to do is to shift to a new coordinate system centered on the center of mass. And then you can look at the relative motion between these two objects. So it's in fact reduces to a one-body problem. That's quite easy to solve if you know how to solve that one-body problem, that is. But if you go to a 3-body problem, you cannot simplify things like that anymore. As a matter of fact, physicists have tried for many generations to try to solve 3-body problems. And to this date, there exists no analytical solution to the 3-body problem in general, except for some very special, simple cases. As a matter of fact, the solutions to the 3-body problem are far more complicated than the 2-body problem. You know, look at the two-body problem. Basically, any 2 objects, attracting each other via the force of gravity, they will just revolve around each other. Actually, revolve about the common center of mass of the 2 bodies if they move relative to each other. Otherwise, they would just fall into each other in a straight line. And that's not sustainable, of course. In the case of 3 bodies, the situation is far more complicated, and the solution can also be chaotic. And that is, if you find a solution that seems to be simple, at some point, if one of the objects get a slight disturbance, that can throw the entire system into chaos. Okay, it's a very complicated problem. In fact, a few years ago, scientists used a supercomputer to solve for some possible outcomes of the 3-body problem. And guess what? They found over 1,300 cases where a 3-body system can evolve according to the force of gravity between them and eventually come back to where they started, which means it's a periodic motion. But there are over 1,300 different patterns. We're not talking about circular motion at all. We're talking about periodic motion, okay? And that's done by a supercomputer, and it's not nearly the total number of possible solutions, which very likely will be infinity. Okay, so needless to say, it's a very chaotic situation, very difficult to predict. Now imagine if you are a planet within the gravitational pull of these three suns, what's going to happen to you? It's not funny. Okay, so we have, we can write down the equations governing the 3-body problem. Suppose these are the 3 stars, 1, 2, and 3. And I observe these 3 stars from a point O. I can find the position vector at the center of each of these three suns using R1, R2, and R3. Then I find that the acceleration of R1, okay, this term, the first term of the left-hand side of the equation, that is the acceleration of the first sun is governed by the force from the other 2. Okay, governed by the force from the other 2. So here's the force from the second sun, here's the force from the third sun, and so on. Okay, the solution to this set of equation in general, we have never obtained the analytical expression, but there are many, many complicated solutions that you can find numerically, maybe by a supercomputer. So if you were a lone planet that live nearby, okay, so you're here. So you are subject to all the three forces from these three objects. And if these three objects themselves move randomly because of the mutual attraction, you can imagine, you'll be pulled in and pushed out, so it's very hard to predict how you're going to move. Okay. And somehow there was an advanced civilization that lived on that planet of the trisolar system. Unfortunately, life was not easy for the aliens on that planet because they could not predict what was going to happen to them. Are they going to be pulled too close to one of the stars so that they get very hot, or are they going to be pushed further away to become very cold? The weather can be very extreme and unpredictable. And because of that, to ensure their own survival, they have to work extremely hard. So they work very hard, and they have developed a highly advanced civilization with technologies way beyond Earthlings. Okay, and somehow they discovered us, the Earth, and to their delight, we're only 4 light years away. And so they were able to build large-scale, very fast spaceships that could reach us in a matter of 200 years. And humans found that plot. So humans have to come up with a strategy to defend ourselves, even though our technology is far less advanced than them. It's actually it's actually a trilogy. This is the title of the first book, and then you have the other two. It's just a fascinating story in terms of sci-fi writing. It's an award-winning novel. But we're not talking about the novel here. We just talk about the complexity of the three-body problem. Okay, so there are some special cases where the three-body problem becomes relatively simple to solve. In fact, I have listed a special case right here. So you have 3 identical masses. Okay, so you got 3 stars, 3 planets. They happen to have the exact same mass, and they're positioned at the 3 corners of a equilateral triangle of side lengths L. Okay, now they revolve, each move like this. Move this way, and this guy moves this way, and this guy moves this way with the same speed v. Okay, so each is doing circular motion. It's very simple to solve. You can easily find the speed of that circular motion, the period of each object going around this circle. And the reason why it's so simple is because of the symmetry. You look at the force exerted on the top mass from the other 2. You got F1 and F2, right? And by symmetry, F1 and F2 have the same magnitude because they have the same distance L from these other 2 objects, F1 and F2. And so when you add F1 and F2, these 2 vectors, you're going to end up with something like this. You add with this force. Okay? Let me draw it more carefully. You're going to end up with this force. This force happens to be pointing to the center of that circle right here. So it serves as centripetal force for this object or this planet to move around the center of that circle. And the same thing can be said for the other 2 planets. So they remain a distance L from one another, revolving at the same exact speed, either all counterclockwise or clockwise. They all have the same period and so on. It's a very simple and elegant solution. But of course, that's a very special case. You got 3 identical planets or 3 identical stars separated by the same exact distance. I mean, how likely is that going to happen, right? But what I want to say is that there are special solutions that are rather simple, but the general solution cannot be obtained. We have never found any general analytical solution except numerical solutions done by computers. Okay, and the situation can be very chaotic. All right, so that is the reason why the aliens on that planet, life was not easy for them, so they were so motivated to get out of their trisolar system and find something more inhabitable, such as the Earth. So their job was to come over and take our planet under their control, so they can live happily ever after. Of course, that doesn't go well with most of the Earthlings, so we have to fight back. And how do we do that? Well, if you read that novel, you probably will find out. But that's not part of the assignment for this course. So let's move on. Okay, let's move on. Another subject that I really want to talk about is the so-called Lagrange points. Lagrange points. What are Lagrange points? Look at a system of two celestial objects attracting each other, so they revolve around the center of gravity of the system. You can think of the Earth and Sun, for example. Okay, consider a system like that. For example, we're on Earth. We look at our Sun, and we are in a circular orbit around the Sun. Since the Sun is a lot more massive than the Earth, you can pretty much think of the center of mass as right on the Sun, and therefore, the Earth simply goes around the Sun, which can be thought of as fixed. A Lagrange point is a point that revolves around such that when you place an object at that point, the combined gravitational attraction of the Earth and the Sun will cause that point to revolve around the Sun, or more precisely about the center of mass of the Earth-Sun system, at the same exact period as the Earth. Therefore, from our perspective, this object appears to be fixed in that location. Okay, because it takes us 1 year to go around, and also takes that probe placed at that point to go around also in 1 year. So it doesn't appear to be moving relative to us. So you can think of it as a, figuratively speaking, a parking spot in space. Once you put something there, it's parked. It doesn't move. It doesn't appear to be moving to us. Okay, that's called a Lagrange point. And for each such system made of two celestial bodies, there are 5 Lagrange points, labeled as L1 through L5. 3 out of these 5 points are on the line connecting these two celestial bodies. You can see in this diagram, you have L1, L2, and L3. Okay, the center in this diagram is the Sun, and the Earth is the other celestial object. And then there are 2 more Lagrange points, L4 and L5. And they are really interesting, L4 and L5. In fact, they are located at a corner of an equilateral triangle formed by the Sun, the Earth, and that Lagrange point. For example, L4, the Earth and the Sun are at the corners of an equilateral triangle. Same thing can be said for L5. Okay, we're not going to focus our attention on L4 and L5. We're going to mostly talk about the other 3 Lagrange points, especially L1. Reason why a space probe placed at L1 will move with the same exact period as the Earth going around the Sun is because the Sun pulls it in. The Earth actually at L1 tends to pull it out of the circular motion, right? It's the force from the Earth is away from the center of the circular motion, but the Sun wins the race because the Sun has a greater attractive force. The overall force points towards the Sun, and the overall force is just right. It has the right magnitude so that this probe will move around the Sun with a period that's exactly the same as that of the Earth. Now, you notice that violates Kepler's third law. Okay, Kepler's third law says if you consider 2 objects, both revolving around the Sun, their period and their orbital radius satisfy a connection, right? T squared equal the same constant times all to the power 3. Clearly, for this probe, the radius of its orbital motion, r, is less than that of the Earth, right? Because L1 is closer to the sun than the Earth. So therefore, we should expect a shorter period. How come that's the same period? Well, it's because, don't forget, Kepler's third law assumed there is only one center of attraction, such as the sun, such as the Earth. But here you got two objects, both the Earth and the sun. They're both attracting the probe placed at L1. And in fact, the effect of the Earth is that it weakens the overall gravitational pull, right? Because it's opposite to the sun's gravitational pull. So as a result, you get less centripetal force, therefore you're going to move slower than expected. And if you place this probe at the right point, L1, the period is not too long and not too short. It's just equal to that of the Earth. Okay, so let's focus on L1. Let's find the distance between L1 and the center of the Earth. Okay, so you launch a probe this far from the center of the Earth, it's going to be parked there. It will revolve around the sun at the same rate as the Earth. So when you look at the sky at that particular point, you can always see that object. It doesn't appear to be moving to us. All right, so let's find that distance. All right, so here's a diagram. Suppose I have placed an object at L1. Okay, could be a space probe, could be anything. And then it's being attracted towards the sun with a force of Fs. It is also being attracted towards the Earth with the force of Fe. And clearly these two forces are opposite to each other. And the net force is therefore Fs minus Fe, right? Let me write that down. So you got Fs minus Fe, that is the net force. That net force equals the centripetal force needed for this thing to move in a circle of radius what? Big R minus small r, okay? Big R is the Earth to sun distance, otherwise known as 1 astronomical unit, and small r is the distance between the center of the Earth and that probe at L1. I just want to find what r is, small r is. Okay, now let me write down the expression for Fs and Fe. We have all learned that before, right? So Fs is equal to G times the mass of the sun divided by distance between this probe and the center of the sun, big R minus small r squared, right? And that force points into the center of the circle, so it's positive, and then minus the force from the Earth, which actually pulls it away from the center of the circle. And that is G times the mass. Don't forget, here is the mass of the probe, small m. Here's mass of the Earth, and then mass of the probe divided by small r squared, right? And what does that equal to? That equals to the centripetal force needed for circular motion. So it's mass times v squared over the radius. That's the radius. Now, remember, I want this motion to have the same period, t, as that of the Earth. So I'm going to rewrite v in terms of t. So we know that v equals to circumference over period. So 2 pi times the radius, which is big R minus small r, over t. This t is 1 Earth here, okay? So you plug that in, and you're going to get the following. You're going to get 4 pi squared m, and then big R minus small r over t squared. Okay. Now, t, again, is the period of the Earth going around the sun, and I know how to calculate t. I can express it in terms of mass of the Earth, mass of the sun, and so on. We did that before, and that, in fact, is Kepler's third law. So what? According to Kepler's third law, I know for Earth going around the sun, I know that t squared equals a constant times r to the power 3, and that constant, we have done that many times, is 4 pi squared over gm. This m is the mass of the center of attraction, which is the sun in this case, and then r to the power 3. R is the big R is the orbital radius of the Earth. That's Kepler's third law, right? Now, if we plug that into this expression here, you plug that into the expression to replace that t squared, and then you're going to get something like this. Okay, So I can now rewrite it as G, mass of the sun, mass of the probe, over its radius, its distance squared to the sun, then minus G ME times the mass of the probe divided by R squared. And that equals to, okay, plug in T squared expression, and I'm going to get G mass of the sun and big R minus small r divided by big R to the power 3. Okay, big R to the power 3. Again, my job is to find small. Now, in general, this is not an easy problem to solve because look, you have R squared in the denominator, and the first term is even worse because you expand into 3 terms, and you also have an R in the numerator. This is beyond a quadratic equation, which you can easily solve. But we're going to give it a shot at a special case, which is certainly valid for the Earth-Sun system, and that is the mass of the sun is so much greater than the mass of the Earth, and therefore the probe has to be very close to, much closer to the Earth than the sun, right? Because the sun is so massive. I mean, if you put this thing midway between the Earth and the sun, okay, and the sun being so massive provides an overwhelmingly large amount of attraction than the Earth. You can pretty much ignore the attraction of the Earth, and then it's going to have a much shorter period than the Earth because of Kepler's third law. You can ignore the force of gravity from the Earth. And the reason why the Earth's gravity plays a meaningful role here is because L1 is much closer to the Earth than to the sun. Okay, so we can imagine small r to be a lot less than big R because the mass of the Earth is much less than the mass of the sun. And then if you use that approximation, can you solve this equation with that approximation? The answer is yes, we can do that. Okay, so to make things a little bit easier, let's introduce a symbol here. Let's introduce the symbol x. So let x be defined as small r over big R. Now we know x is far less than 1. Okay, we know that for a fact for the Earth to Sun system. And then I'm going to cross out some common terms. Okay, I'm going to cross out this big G here, this big G here, this big G here. And there is also a mass. I forgot this mass of the probe here, the mass of the probe here, which I can also cross. Of course, the mass of probe doesn't matter. Anything powered by gravity, the motion has nothing to do with its own mass. Okay, and then you have small and big R. What I'm going to do is I'm going to take 1 over big R squared out of each term. Okay. So for each term, I'm going to factor out a common factor 1 over big R squared. And then what's left for the first term on the left-hand side is just ms in the numerator. And then in the denominator, I already pulled out 1 over, already pulled out big R squared. So what's left is 1 minus small r over big R, which is x, and then squared. Okay. There's a big R squared. I didn't even bother to write down the big R squared here because it's going to cancel with the other, was the big R squared from the other 2 terms. So the next term is minus me divided by what? Again, you factor out a big R squared, what you're left is small r over big R squared, which is just x squared. Okay. And then that equals to what? You got still ms left. Okay. Factor out 1 over big R squared. You still have 1 big R left in the denominator, and the numerator is big R minus small r. So you work that out, and that is 1 minus x, isn't it? Okay. Doesn't write very well for some reason. 1 minus x. All right. My job is to find x. Now, again, this is not easy to solve, so I'm going to have to make some approximation here. There is a famous expression for approximation 1 plus x to the power n. We've done that before, to the power n. When x is very close to 0, it is roughly equal to 1 plus nx. We've used that before, and we'll be using that later. So it's very handy, okay? When absolute value of x is much closer to 0 than to 1. So I'm going to apply that to the denominator in the first term on the right-hand side. So therefore, I have 1 minus x to the power -2, right? Because in the denominator, isn't that equal to roughly 1 minus 2x? With n equal to what? -2, okay? So with that approximation, and then I can replace the first term as ms times 1 minus 2x, right? 1 minus 2x, instead of 1 over 1 minus x squared. And the next term, I'm just going to keep, okay? me divided by x squared. And then this becomes approximate, okay? ms and then 1 minus x. Yeah. Now, the rest is really straightforward. You notice that there's ms on the left-hand side, this term, combined with ms, and there's also an ms on the right-hand side. These two cancel out, okay? What's left is -2 ms x minus me over x squared. That's equal to roughly -msx. Right? Actually, I made a little mistake here. Over here, let me use a different color to correct myself. 1 minus x to the power -2 is actually roughly 1 plus 2x, okay? Because it's minus x, not plus x, right? So you already have a, so when you apply this approximation here, when you see x here, when you see this x here, you should replace with -x because there's a negative sign here. And there's another n, which is -2 in this case. It's -1 times -2, it's 1 plus 2x. Sorry about that. And with that, you can rewrite this is 1 plus x. Okay, so there's a positive sign here. And then, we're just solving for x and just multiply everything by x to the power 2 to get rid of that x squared in the denominator. And then you can easily find the solution. Okay, so it becomes a piece of cake now. The answer is now x roughly equal to me over 3ms to the power 1/3. That is the approximate solution, okay? And indeed, it is a lot less than 1 because look, you have me in the numerator and 3ms in the denominators. Clearly, it's a lot less than 1. Therefore, our solution is self-consistent, meaning that we assumed x to be very small, use that assumption to found x, and indeed, we found this x to be very small. So it's self-consistent. Okay, but what is x anyway? X equals to small r over big R. That's the definition. So that tells me what small r is. And so small r is roughly equal to big R times the triple root of me over 3ms. Okay, so let's work this out numerically. We plug in the mass of the Earth, the mass of the sun, and then we found this ratio to be roughly 0.01. So this is an important result, numerical result, 0.01 R. The Earth to Sun distance, big R, is also otherwise known as 1 AU, astronomical unit. Okay, 0.01 AU. And how much is that? That is 1.5 million kilometers, which is 1.5 times 10 to the 9 meters, okay? 1 astronomical unit is 1.5 times 10 to the 11 meters. That's the Earth to Sun mean distance. Okay, so what did that tell you? It tells you that for the Earth to Sun, Earth and Sun system, L1, okay, L1, this is L1 right here. Let me highlight it. L1 right here. Is from the Earth is 1% of the way out to the Sun. So therefore, you know, if you start from the Earth, center of the Earth, you launch a probe to L1, it is only 1% of its way to the Sun. It's very close to the Earth compared with the Sun, but still it's 1.5 million kilometers away already. So that's L1. All right, now how do you find L2? Well, L2 is another Lagrange point. So at L2, the force from the Sun, the force from the Earth, both point toward the center of its circular motion, which is pretty close at the center of the Sun. And you can use that formula to calculate the location of L2. All you have to do really is look at this formula here. You got to change the sign here. Okay. You got to change this sign here because the forces from the Earth and from the Sun are now together. And here is actually big R plus small r. Okay, small r being the distance from L2 to the center of the Earth. So these are some changes. The answer will be different, but I'm not going to repeat this pretty much the same idea of calculation. But I do want to talk about the utility of these Lagrange points. L1 is an ideal spot to place an observer for the Sun. Imagine launch a probe that is aimed at monitoring our Sun. Okay, this probe, when launched to L1, will appear to be fixed to an earthbound observer. You know, you can just, you know, you can expect the thing to be always there as if it's parked, because it's actually moving in sync with the Earth around the Sun. And it's always facing the Sun. It's never in the shadow of the Earth. And plus, it's also, you know, the signal is always observed during the daytime. Okay, so you know, so that really is quite an ideal spot to launch a Sun probe. And guess what? Since 1978, multiple probes have been launched to this spot L1 to observe our Sun. L2 is also important, along with L3 and so on. The L4 and L5 are more interesting, and the reason why they are also Lagrange points is something I want you to think about. Okay, why this equilateral triangle? If you launch a probe to place at L4, for example, it doesn't receive the same amount of force from the Earth and the Sun, obviously, but the distance is the same, right? To the Sun and to the Earth. Therefore, the force exerted on an object from the Sun to, you know, for this object placed at L4, the force from the Sun and force from the Earth, they're not equal, but their ratio will be the same as the ratio of the masses, don't you think? Okay, if the Sun is 100 times more massive than the Earth, which of course is even more than that, then the force from the Sun at location L4 is 100 times more than that from the Earth. Why is that significant? How does that lead to another point, another Lagrange point on which the object placed there will be moving with the same period t as the Earth? That's something you want to think about. Okay. What I want to talk about also is the Lagrange points for the Earth and Moon system, especially L1. Now, the Moon is smaller and less massive than the Earth, but the difference is not that much compared with the Earth and Sun system. Yeah, the Moon is about 1/3 the size of the Earth. Okay, it is not that lighter compared with the Earth. It's not that less massive compared with the Earth. And as such, L1 between the Earth and the Moon, if you launch a probe towards the Moon and you park it at L1 between the Earth and the Moon, that distance should be actually further out. Because look, you're looking at a case where the Moon is attracted, the Earth also attracted the Earth wins the race. But do you need to launch that probe that close to the moon? No, because the moon, again, is not that much less massive compared with the Earth, as the Earth compares with the sun, okay? So L1 for the moon, of course, it's closer to the moon than to the Earth. It's just like, L1 for the Earth is closer to the Earth than to the sun. It's always closer to the less massive object, okay? But how much close? How much closer? It's not 1% of the way out. It's about 15% of the way. Okay, so L1 for the moon is about 330,000 kilometers from the Earth, and the Earth to sun, Earth to moon distance is about 380,000 kilometers. So again, small r is about 15% of big R in this case, unlike the Earth to sun case, which is 1% of the big R, because of a huge mass difference between the Earth and the sun. And this point L1 for the Earth to moon system is also interesting, because once again, if we launch something there, this object appears to be fixed in orbit between the Earth and the moon. We can always observe it. It doesn't appear to be moving. And that's interesting because that becomes a staging ground. If we want to transport some materials to the moon, we don't have to go all the way to the moon in one go. We can just simply put something over there at the L1, and it's not going anywhere, right? Because it's just moving in sync with the Earth and the moon. It will always be at that spot. Okay, so that besides as a observation ground, observation spot, you can also use that as a staging ground. That's like the ultimate parking space. Okay, so that's some simple discussions about the Lagrange points, and there are many other applications, and there is also the issue of how stable these points are. Those things are beyond the scope of this lecture. So this is our series of lectures about universal gravitation, and there are tons of other things to be explored. And if you're interested, there are many literatures you can access. But needless to say, you can see we're only seeing a very small part of this fascinating subject in this course.